Okay, so let's continue. Let's start with the second part of this, where we'll create a factory contract first and then a factory of factory contracts. Let's call it deployer. Takes in some of the same things. Define a version for Solidity, Pragma, and then use opens Zeppelin contract. Herein what we need is ownable. We'll import the two burner contracts that we have defined. And we'll define that the contract deployer is ownable. To start with, we'll have a default value of the contract status as paused. And we have a function pause contract which can be called by the owner only. To modify the state from paused to unpaused and vice versa. Then we have a couple more functions. One is going to be your predict address, which will create the burner or the contract address to which the payment will go, and one is going to be your deploy function. Now let's get into the predict address function and see what it does. What is the error? Writing a quick doc string. So the function is predict address, creates the burner contract address. Okay, so let's now figure out what are the parameters that we'll need. So we need every address to be unique. We need to pass in something called salt, which will make sure that every address is unique from each other. Then we need the token address. In the case of ERC20 tokens, we need what is the amount that has been requested. We need the merchant address, and we need the payment processor address. What we'll be using is an order ID provided by the merchant to link that to the burner address. Now let's quickly put in the relevant types. So this can just be string. Token address will be an address. This is going to be uint 6. Right. So whenever this function is called, if the contract is paused, we need to revert with a paused contract error. Now generating write code for native burner. We'll just do an ABI dot encode pact. And we'll pass in the native burner here. Then we need to pass in the relevant constructor parameters. Which are ABI encoded. We do the same for the ERC20 contract. ERC20 burner address. Right. Now since we are using the same predict address method to basically figure out and like create this for either native as well as ERC20, we need a way to differentiate that. So what we do is provide in a flag. I think this can be implemented better here, and I'll just use what we have been using so far, that whenever we are calling for a native token, what we do is pass the token address as 0 address into the predict address function. What we can also do is have like two different functions or another flag in here. Yes, I got a bit distracted with a couple of messages. Let's get back. Yes. So since we are using the same function, all we do, it was kind of a hacky way we can improve upon this, that we can either separate out the functions itself. But for now, if the token address being received was the 0 address, it would go into this native contract bytecode, and if it was the token address was not 0, then it would use this particular then we take a hash of this. Right. Somehow the auto formatting is not working for me. That is a bit annoying. I think it is. I just overextended it. Yes, this works fine. Once this hash is calculated, we return the address calculated, which is uint 160, uint of the hash. Now there are a bunch of optimizations that I think we can do here. One is separating out the function altogether. Another one would be this particular piece of code. I'm just doing a small housekeeping thing. Continue after that. Okay, so we have a predict address. Now this is the function that the merchant's backend calls with a particular order ID to generate a unique address on which the payment is to be received with the requested amount, merchant address, and the payment processor address. Now once this is done, what the merchant does is, or the backend will keep checking for the balance of that particular native burner or that particular ERC20 burner in the given token address, and if the balance is sufficient, it will call the deploy function, which will deploy the native burner and the ERC20 burner addresses and settle and send the funds eventually to the given merchant address. So let's quickly complete this piece. Deploy function is again very similar. It will take everything that predict address does, because these are identical with respect to params, etc. Only difference is with respect to what happens at the end of this call. This function is public, but only the owner of this contract can call this. The contract is paused, we need to revert with paused contract. Else if, now again we, based on the token address that we provide in the call, we need to check if this is the 0 address, then we know it's a call for a native burner. Can instantiate our native burner instance. And in the constructor we'll pass in the relevant parameters. First we need the salt as we have provided in the predict address. Once this is done, we just called in instantiated it, meaning deployed this particular native burner contract, and we return the address deployed. If it's not address zero, then all we need to do is, then we now know that it's a ERC20 burner contract. Pass in the salt. Then pass in the 4 parameters. Once this is done, we'll just return the current address. And this is it. This is the crux of the payments flow that you need. Now the things that we can do here is we can also like emit events from here. Unsuccessful deployment, the burner address. I think this is something that I'll explore as well. The advantages of this versus just calling this contract from some sort of backend or UI and figuring out the status. The events might not be necessary, and then we'll need to also add all the add params on custom splitting logic as well. The other bunch of things that we will be going to do. Now one more thing I think this contract needs is, yes, make it customizable. Basically have its own constructor which is called by factory of deployers and pass in attributes for the organization, business, calling it. Can have something like company name, and other such params. Symbol, logo, their address, etc. So this is all hard coded, so basically enhance security. Alright, we'll continue with the factory of deployers in a bit.